All right, so welcome back, everyone. And I think if there are no questions, I will just continue further. I hope that you can hear me well and see me. All right, so in the next yes, the video is being recorded. All right, so in the next part, I'm going to be talking about the derivation of rigid body dynamics, equations of motion, and still here we're doing nothing with underwater, with the underwater domain. And then the last part, the hydrodynamic effects, is when we're going to talk about the introduction of forces that are caused by hydrodynamic forces. All right, so rigid body dynamics is basically also just a bit of a revision of the Newton-Euler formulation of a body that is moving in space, a rigid body moving in a 3D space. Just to recall the very simple Newton's second law. So if a body is moving in an inertial frame, the velocity of its center of gravity, or the acceleration of its center of gravity by the mass of the robot, is going to be equal to the forces that this body is experiencing. So if this force is equal to 0, of course, the body is either not moving or just moving at a constant speed, which is Newton's force law. So another axiom are basically, or the two first and second Euler's axioms, which is kind of the extension of Newton's second law that formulates the motion on a body basically with respect to linear and angular momenta. So the linear momentum g, so the subscript here means that it's at the center of gravity of the body. So the time derivative of the linear momentum is equal to the force applied on a body, and the linear momentum is the mass by this force Fg, and the time derivative of the angular momentum, sorry, here's a small mistake, this should be the velocity, the linear velocity, and then the angular momentum, L, so the time derivative of L is also going to be equal to the moments that the body is experiencing, and this angular momentum is the moment of inertia around the center of gravity by the vector omega b, which is the angular velocity of that vector. So let's take a simple body here, a body of an underwater vehicle, for example, and what we're trying to do here is basically to derive the equations of motion about an arbitrary point, so not about the center of gravity, and which is something that we usually do in underwater robotics that is not often done like in terrestrial robots or manipulators. And the reason for that is that this center of gravity location might change. That could be either because of some payload that has been changed, or usually we design underwater robots so that the center of gravity is a little bit placed lower in the body, so we shift it a little bit down to keep a bit of stability. And sometimes, like, it's easier to also model the hydrodynamic forces with respect to the geometric center of the body rather than the center of gravity. So this is what basically we'll be doing here briefly. So first of all, let's define an inertial frame with the center OI, and then an arbitrary origin point OB on the body frame, and the center of gravity is going to be G. And we were just going to have this following geometric representation of the vectors RB, RIG, and RG. And what we want to try to do is to compute the acceleration of the center of gravity in the inertial frame in terms of the velocity and acceleration of the body frame. So just from the figure, we can see that this vector RIG is equal to RB plus RG. So this vector here is just the summation of those two vectors. And assuming that the body is also rotating with an angular velocity, if we take the time derivatives of this relation here, so another assumption is that this at the moment that we are deriving these equations, the center of gravity, or this RG vector, is fixed. So the center of gravity is not moving. So basically the time derivative of RG itself is 0. And then we're going to arrive at this formula. So basically the velocity of point G with respect to the inertial frame, or here, sorry, we're still not talking about any frames. We're just talking, this is valid in any frame. So the velocity vector IG is the velocity, is the VB, or the V of the origin, plus, since this body is rotating with a certain angular velocity, is basically the angular velocity cross this vector RG here. So basically, if the center of gravity is exactly, or if we choose OB to be the center of gravity, then this term will disappear. So now let's decompose this relation in the body frame. So as I said, this relation is valid in any frame because it's just a geometric relation. So if we decompose it in the body frame, then the VIG in body frame is equal to VB, or the center of the body, plus the angular velocity cross RG expressed in the body frame. Okay, so taking this relation, so of course here the superscript B denotes that which coordinate frame we are expressing these relations in. So now let's transform this back to the inertial frame, which basically would just multiply by the rotation matrix from the body to the inertial frame. So this VIG in the inertial frame is just R from B to I multiplied by this term here. So if we just substitute, we get this formula. So the rotation matrix plus VB comes down here, and this term comes down here. Now, note that if we take the, since I mean, as I mentioned also before, this time derivative of this vector RGB, no matter in which frame it is, it's going to be 0. And the time derivative of the rotation matrix is going to be given by this formula here. So it's the rotation matrix times this Q of omega in body frame. Okay, so if we calculate the time derivative, here's a little bit of mathematics. I'm not going to go through it in much details, but basically the only thing that we're trying to do here is from this relation we get the time derivative. So as I mentioned in the beginning, we are interested in calculating the acceleration because we want to apply Newton's second formula. So if we take the time derivative of that using these terms here, we can just expand this, and then if we cancel out all the 0 terms and replace the time derivative of the rotation matrix by the value here, we will arrive finally at a formula which is basically the rotation matrix multiplied by the acceleration, the linear acceleration basically, then the angular acceleration cross product with this RGB, or the vector of the center of gravity, plus these 2 terms here, which is basically, if you can see here, this is nothing but the cross product between the linear and angular velocity, which is the Coriolis term. So if anybody is moving with a certain angular velocity, it will experience a certain force on it. And this part here is just the part that is introduced because we are deriving these equations not with respect to the center of gravity. So if RG is 0, this term would go away. This is what we call the centripetal Newton's second law, basically, that mass by the acceleration on the center of gravity with respect to the inertial frame is the forces that are applied on the center of gravity also with respect to the inertial frame. So if we take that guy here and then substitute it here, so in this case, of course, the acceleration is VI g dot, and then we just left multiply by the transpose of R. So this transforms the forces also from the inertial frame to the body frame, and then we will be able to get rid of this part here. So we will only be left with that part. I hope I'm not too fast. Exactly, so that's the equation that we will arrive 2 in the end. Now, if we just take these terms and then replace the notation that we defined earlier, so the only thing is that omega, sorry, before that, again, I already talked about it. So if we choose the center of the, or the origin of the frame B to be the center of gravity, this means that this vector here is 0, and that V of B within the body frame is the same as V of G in the body frame. So this term here disappears, as well as this term here. Right, and finally, if we just substitute, or we use the nomenclature that we defined earlier, so the velocity or the linear velocity in the body frame is just this vector here, u, and the angular velocity in the body frame is just simply omega. We will finally arrive at these kind of equations of motion. So the mass multiplied by the linear acceleration plus the angular acceleration cross product with the vector which describes the center of gravity in the body frame, which basically, I mean, if you think about it here, this is just like the mass matrix, and this adds a little bit of an off-diagonal term. And this part here is, again, the Coriolis part, and this is the centripetal part. This is going to be equal to tau1, which is the linear forces applied on the body frame. So this is for linear motion. Now, for angular motion, it's a little bit more complicated. I'm gonna just give a brief introduction, but kind of the methodology is almost the same. So we always want to try to calculate the angular acceleration with respect to the center of gravity in the inertial frame, right? So first of all, let's just define these terms. So the linear and the angular momentum around point O. So if we consider here an element volume that has a certain velocity Vp, then we have our origin here as well with the velocity Vo and the center of gravity with the velocity Vg. And then we have these relations. So we have the vector R0 and vector R and Rg. So R basically here is a variable vector because we are basically integrating this element throughout the whole volume of the body, which basically will give us in the end just the definition of angular momentum with respect to each point here. So this is the angular momentum with respect to the point O, and this is the angular momentum, or OB, and this is the angular momentum with respect to the point G. Sorry, this is not with respect to the point OB, this is with respect to this point here. All right, so basically also from the figure, we have RO is equal to RG plus this term here R. And then if we just expand, if we take that term, plug it in here, we will basically arrive to this. So basically this is nothing but that term here. So this is LO. And this basically, if we just do this integral, so this is now becomes independent because RG is a fixed vector. So if we just do the integral of this velocity multiplied by the rho, or the density of the body, times this element volume across the whole volume, then we will just get the mass. And then these values just hold. Now, again, the Euler's second axiom about for angular momentum about the point OB. So that's going to be the moment of inertia about this point multiplied by the angular velocity plus the since we are trying to derive this angular momentum not with respect to the center of vector Rg, which is the center of gravity, cross product with this velocity vector V0. that we did first. So this relation holds in any frame. If we decompose this in the body frame, then we just add the superscript here, b, and that will be here the angular velocity in the body frame, and this would be the velocity VO in the body frame, or the velocity of the point OB in the body frame. So from here onwards, I'm not going to put the whole mathematical formulation. It's a little bit long, and I don't want to bore you to death. So if you are interested in this full formulation, I think you can check out, like, in the appendix of my PhD thesis, I did that kind of in details. But as I said, what we're just trying to do here is we want to get the time derivative of this moment or angular momentum, and then transform it to the inertial frame to be able to apply Euler's second axiom. If we do all of that, we will arrive at something very similar to what we had in the linear part. So here we will arrive at this point here. So basically the moment of inertia with respect to point O multiplied by the angular acceleration in the body frame, plus the angular velocity cross product with that term here, plus the mass by the vector RGB, also multiplying this big term here, which is also, again, this is nothing but a centripetal force, just because the center of gravity is not at the point that we are measuring, so we will always experience this centripetal force if the body is rotating. And this is also just the Coriolis term. So again, if we take the nomenclature that we had before, this omega IBB, just we say it's omega, and this velocity vector in body frame is just v dot, basically. So we will have finally that equation over here. Now, if we take, if we align those two, so far we have the linear part and the angular part. So the linear part describes linear acceleration. So you can see here, just by introducing this shift in the point that we're trying to derive the equations of motion on, we will always get off-diagonal terms in the inertia matrix, because this is basically still a function of the acceleration, and multiplying this term here, which is like the position of the center of gravity. The same thing we will find here. So you can see that these terms are actually the same. So the off-diagonal terms of the inertia matrix are kind of the same. So this m multiplies that part here. And if we take those and we like expand them, we can rewrite them in a bit nicer form rather than this complicated form here. So we can just write them as an inertia matrix multiplying the accelerations plus a matrix which describe the Coriolis and the centripetal forces. That is a function actually of the linear and angular velocities in the body frame. That would be, so this m plus times acceleration plus this Coriolis and centripetal terms are going to be equal to the other forces that are applied on the body. So these other forces, we're going to see exactly what they are. So they are not just actuation forces, but actuation forces plus all of the hydrodynamic effects that are going to be introduced by putting the body in the water. And just to give the shape of these matrices, so as we saw here, so basically M is here still a positive semi-definite matrix, so it's just the mass by an identity matrix, and here's the moment of inertia, and then these two off-diagonal terms are introduced just by the fact of that we are moving the center of gravity, or no, we're not moving the center of gravity, but we are deriving the equation of motion not on the center of gravity, but on some arbitrary point in the body. And so if this is 0, then we go back to our classical mass or inertia matrix. And the Coriolis and centripetal forces are gonna be of that form. So also here, so Coriolis we will always have Coriolis forces because it's basically just a body with an angular rotation that is moving with a certain velocity. So we will always get these terms here. However, if this extra centripetal term is just caused by the vector RG. Okay. Any questions before moving on to the hydrodynamics? Okay. If there are no questions, then I'm just gonna move on to the hydrodynamic effects. So basically, one of the simplest forces that anybody is going to experience when we just put it in the water is what we call here restoring effects. So the weight is one of the forces that it will always have, because then it's a free-floating body. However, there is also another force which is we call the buoyant force. So the weight, first of all, is just the mass by the gravity vector and is always directed towards the center of the Earth, no matter where we put it. So this is always going to be a force that is always in the inertial frame. No matter how you rotate the body, this will always be pointing downwards. The same exact thing is going to be with the buoyant force. So the buoyancy or the buoyant force that the body experiences is going to be projected or is going to be projected exactly on the center of buoyancy. Or if you think about it, what is the center of buoyancy, or how you can find that out? If you have a body and you just assume that the density or this body is homogeneous, so it has a uniform density all over, and just place it in the water, so the volume that this body displaces, the geometric center of that volume is going to be the center of buoyancy. Whereas the center of mass or the center of gravity is something that we can manipulate easier. So basically, if you have a body which is not homogeneous, let's say you have an AUV that the batteries, let's say, are the heaviest part of the AUV, and if you place them below, you're going to be pushing the center of gravity a little bit lower. If you place them above, then you're pushing the center of gravity a little bit above. So exactly, so this basically would cause for us the so-called restoring forces. So this kind of introduces a little bit of stability. It could be also instability if we design our vehicle a bit wrongly. But if the center of gravity is always below the center of buoyancy, this is how we tend to design underwater vehicles, this will have a natural restoring effect, because no matter how you rotate this, these two forces basically, they will, if we just, let's say, assume that the vehicle is how we can see it here, this basically will just have a moment around this point that will restore that body so that these 2 points are aligned on top of each other directly in an inertial frame. Okay, so what we're trying to do, so since we know that these forces are always in the inertial frame, we want to actually transform them to the body frame. And why are we transforming anyway these forces to the body frame? Well, first of all, the damping terms or the hydrodynamic forces that we're gonna see later are way easier if we derive them in the body frame. And all of our actuation is also like all of the actuators that we're gonna see in the second part are always placed on the body. So it's way easier to find the transformation from any actuator to the center of the body or the origin of the body frame that we've chosen. Exactly. So now, as I just mentioned, since these forces are always in the inertial frame, so we're going to express them as the following. So Fg in the inertial frame is just the weight, which could be assumed as a fixed value, multiplying the vector 0, 0, 1 in the inertial frame. It's always along z, pointing down. And as we remember, z, we are using the frame northeast down, so positive z is downwards. And the force caused by the buoyancy is just B, which is the density of the water, the volume that the body is occupying, and the gravity. And this is always going to be pushing upwards. So if we take these two forces and have the transform of the rotation matrix, we can bring them back to the body frame. As simple as that, basically. And then if we just expand these terms, so we will have the final restoring forces and moments in the body frame. So exactly, so if the forces are just going to be the summation of those two terms, this is like the force that they will exert with respect to the center OB, and the moment or the torque that these two forces will exert with respect to this point are basically nothing but the vectors, this RB and RG, cross the force. So that's basically what moment this vector here is exerting with respect to that point, and the same thing for that vector. So this is, as I said, we kind of represent it as the term B, which is always a function of the rotation matrix or the quaternion or the Euler angle, so whatever representation you want to use for describing rotation. Now, before I talk about this disclaimer, so these restoring forces, another thing I forgot to mention, we call them, I mean, they are hydrostatics. They are not really hydrodynamics because they are just a function of the pose. They are a function of the one fixed orientation, right? So they are always going to be static. So the only thing that's changing here is just the rotation matrix. They are not function of velocities. This is what I wanted to say. That's why we call them hydrostatics or accelerations. So the next thing before I start talking about hydrodynamics, just a disclaimer here. So the full analysis of hydrodynamics effects on a body moving in a viscous fluid is basically, to understand that completely, we have to invoke Navier-Stokes equations, which are basically means that we want to solve infinitesimally for every point surrounding, or every point of fluid surrounding the body, to be able to predict what are the forces and moments that will be subjected on this body while moving. However, this is not feasible for any robotic application or for any either control or navigation application, because that requires basically, we can talk about, for example, computational fluid dynamics, so you can make meshes around it. However, you don't want to have a supercomputer on your robot to be able to calculate that quite accurately. So what we are going to be dealing here with are simplifications of these complicated Navier-Stokes equations. So exactly. So one of the first hydrodynamic effects that anybody that will experience is a so-called added mass. This added mass, I mean, you can think about it. Whenever you have a body that is surrounded by a fluid or it's moving within a fluid, it's kind of a virtual mass that is also accelerated with this body once you apply a force on that rigid body. However, please don't think of that as a fixed size or as a fixed volume of water. So this mass is basically just due to the effect of viscosity. So basically, when I take a body and imagine that I want to just accelerate it, so I just give it an impulse. So imagine that there's a body and then you just kick it. You hit it, you take a hammer and then you hit it and it's within the water. So basically what happens is that all of the layers of the fluid or of water that are very close to the body are going to be accelerated way faster, so there will be a higher force, and this force will diffuse the further away you move from the body till it reaches zero, basically. And this is only due to the shear forces or the viscous forces, basically, between, assuming that the water or the fluid is composed out of layers, and there are like these shear forces between those different layers. So exactly, so this is what I just mentioned. So, and these forces are basically going to be opposing, or going to be like reaction forces, equal in magnitude and opposite in direction to the body, basically. And this kind of also introduces an effect which is called a memory effect. So basically, if we think about it, let's assume here that we have like an infinitely long plane, basically, or just an infinitely long rigid body that, and so this is the red part here, and then blue part is the fluid. So as I said, if I give this an impulse, so if I take a hammer and then I just hit it, what will happen is that the velocity of the fluid will be, as I said, the most here, and then it will like diffuse as higher I get. However, this is not gonna just remain like this the whole time. As long as the body moves, these kind of velocities will kind of get smaller in magnitude. However, there will be a bit of a delay. So as this body moves, these velocities or these forces that are these reaction forces are gonna just move up the layers due to these viscous forces. And this is basically, in the end, mathematically, if we want to describe it, is the convolution between this reaction of the body. So this introduces here basically a so-called memory effect, which is we often don't model when we talk about added inertia, because these forces are always going to be a function of the forces that came at a time step before. Okay, so this is like one of the parts of hydrodynamics that if we want to model in a practical manner, we have to simplify. And some of the simplifications that are done here, so basically if you want to consider the hydrodynamic force, let's say along one of the axes, let's just talk about only the x-axis of the vehicle. So this kind of force due to the linear acceleration along this axis only is going to be described as the following. So it's basically just xa is the force. Is going to be minus, since it's opposite in direction, with a certain term xu dot. So this is like a term that multiplies the acceleration, and then this term is basically the partial derivative of x with respect to u dot. So this is with respect to the difference of acceleration. So basically this is only across one dimension. So if we take this and calculate these forces with respect to each other component of velocity, so we have three velocities in three linear velocities and three angular velocities, oh sorry, accelerations we're talking here, not velocities, we can arrive at a full 36 component added mass matrix. Now, of this form basically. So this is here taking the forces that the body is experiencing along the x-axis and calculating the partial derivative with respect to the acceleration on the around the x-axis, the acceleration about the y-axis, and so on. So this basically, these terms are going to be a function of the geometry of the body. Now we can calculate this by using, like, if we have simple geometries, these equations or this Navier-Stokes equation is going to be way simplified, and then we can calculate that this relation kind of quite well. However, when we have a bit more complicated bodies, which is any vehicle, I mean, you don't have a perfect sphere, underwater vehicle, or a perfect cylinder or ellipsoid. These, so I said, these are going to be a bit harder for us to estimate once the geometry of the body is a little bit more complicated. So, as I said, so because of this complicated geometry, this MA is not necessarily a positive semi-definite matrix like the rigid body mass matrix is.
Bilal,
we could, sure.
Bilal, but since we know roughly how this behaves because of these complex equations, couldn't we simply just measure it to obtain an estimation? Yeah. Put it in the water and put some control over it and see how it moves or whatever.
You're spoiling my my presentation. I'm going to be talking about this in a later part of the. So yeah, exactly. So, however, even if you want to measure it, you need to have some sort of, you need to have the form of the equation beforehand. So this description here has to be the more accurate description. However, this xu dot, this is what I just said, is not only a function of, since the fluid is a little bit, since, as I said, it has like this kind of memory effect, it is also a function of time somehow. Right, so if we want to do a system identification, which is what you just been talking about, we need to have we need to start from a description of how much we understand the physics, put it in the water, run some experiments, collect data about it, and then we could try to fit these equations or try to estimate those.
We need to know what to measure, right?
Exactly.
So how many dimensions, etc. There is another question from Jeroen. Maybe he should ask. Just open your mic and speak, I think.
Yes, please.
Thanks.
Anyone, yeah.
Yeah, I had the question, isn't this in a sense the same as like moving through air, but maybe that's negligible?
Yeah, exactly. So it's not exactly the same because air is also compressible. Fluids or water is assumed to be incompressible. So the equations also change a little bit, but Navier-Stokes equations takes care also of the density. So if a fluid is compressible, that will also be taken care of. So usually we neglect them for land robots or some manipulator arm in air because this effect is going to be very low because there's a so-called Stokes number, which describes the viscosity of a certain fluid. So the Stokes number of air is way lower than Stokes number of, let's say, saline water or some certain oil. So that's why we usually tend to ignore them in air.
Okay.
However, in water, they cause way more problems than in air.
Yeah. Okay, thanks.
All right. Any other questions? Okay, then just continue further. So yeah, exactly what I was just saying here. So this mass or this added mass matrix is not a positive semi-definite. However, we can assume it is positive semi-definite if the fluid is ideal, so if it has a fixed density, no currents or waves, and the body has certain symmetries. So, however, this is not the only effect that a mass matrix. I mean, we saw before that if a body is also rotating, it will also have an added Coriolis effect. And the way we're going to derive this Coriolis effect is by using Kirchhoff's equations. By the way, by basically just taking the kinetic energy of the fluid or of the mass moving in this fluid. However, just one note, this thing that we're going to talk about now, you can use the same, the so-called Lagrangian formulation to derive also the rigid body equations of motions, not the Newtonian Euler formulation. Just a note on the side. So let's define again, as I said, the kinetic energy of the body, which is basically just half mv square, or if we are talking about a rigid body, so that's half the velocity transposed by the added mass matrix by the velocity. Now, Kirchhoff's equations basically are also just an extension of the Lagrange equations for a fluid. So if a rigid body moving in an ideal fluid, if we take, first of all, the derivative of the kinetic energy with respect to the velocity, and then also take that term and then get the time derivative. And since it's also moving with an angular velocity, so there's an added term, which is the skew of the, which is basically the angular velocity across that term. So this basically is going to be equal to the force that is acting on the body. You can see here a bit the similarities between this and between the Euler axioms, basically. And if we take that derivative of this term with respect to the angular velocity and then get the time derivative of that, we will also have these additional terms here. This will be equal to the moments that are resulting from this added mass. So if we expand those, sorry, for questions, guys, if you want to ask questions, it's a bit hard for me to read and ask. So you can interrupt me anytime you want and open your mic and speak. But I'm gonna read it briefly, this one. So can we simplify the vehicle shape as cube parallel pipe calculated the added mass? Yes, exactly. I mean, this is what we usually do. This is what we usually do to calculate that. So we simplify those geometries, or we take a complex geometry and then we start to approximate it as a combination of different simple geometries. However, it's not so accurate, and I can tell you that. The better way is to or if it's possible, or if it's feasible, if your vehicle is not so huge or not so expensive to put in the water and collect data from and try to identify that. That is always the better approach. But yeah, this approach is also valid. Okay, so again, moving from these Kirchhoff equations. So if we just rearrange those, we expand them first, calculate the time derivatives of this kinetic energy, and then we rearrange them, we could arrive at a very similar term with respect to the rigid body equations. So here basically we will have MA, or the added inertia matrix, by the acceleration, and a term which is basically here just Coriolis terms by as a function of the velocity multiplied by the velocity vector. And this Coriolis matrix, basically we can get it according to this formula. So basically these A11, A12 are just the submatrices of the full mass matrix. And again, if the fluid is ideal, this Coriolis term has this skew symmetry property, so it's equal to minus CA transpose. All right, so this is added mass or added inertia, which is, again, we will see later that these terms are like not at all negligible when it comes to underwater vehicles. They can sometimes, this added matrix, depending on the geometry of the body, can be as if we are virtually trying to accelerate the double of so like as if we are doubling the actual inertia of the vehicle when it's moving in air, if we put it under the water. All right, so here is what I think Matthias was just asking. So here are some of, if we have these simplified equations for simple geometrical shapes, for example, a cylinder, we can easily derive the equations of added mass, assuming, of course, an ideal fluid. Now you can see how, I mean, here is quite simple for a cylinder. So, and since it also has planes of symmetry, so for example, this term, so this will be only, like all of the off-diagonal terms will cancel to 0 because it has all these symmetries. And we will only have a diagonal added mass matrix of these, using these equations, like by the length, by the radius of the cylinder, we can derive them. However, if we take a look at look how complicated it becomes when we talk about an ellipsoid. So this is also an ellipsoid of a fixed radius b, so it's not an ellipse that is like spanning this x-axis. And you can see how like these equations become way more complicated. And imagine this for a more complex object. All right, so that's it for added inertia. Now, one of the other terms that we have, which is also plays a huge role, is the damping. So damping is actually one of the most complex, even more complicated than the added inertia, and the hardest to model among all the underlying physical phenomena that occur when we are accelerating or when we are pushing a body in a water. So according to one of the books that I just mentioned earlier in the chat, Fassen, we can classify the causes of this damping with 4 main, let's say, damping sources. First of all, so-called potential damping. So this is kind of encountered when we have a body oscillating with a certain wave excitation frequency. This is called potential damping. For underwater vehicles, assuming that these vehicles are way below the surface or at a range below the surface where waves are not effective, we usually ignore it. However, you should not ignore it for surface vehicles. Another term, which is the most dominant part if we are talking about a vehicle moving at a slow speed, is the viscous skin friction. So this is the shear force just by moving with a fixed velocity, what is the force that is kind of causing friction on the body. Usually we model this as a linear relation to the velocity if we have a laminar flow, or quadratic if we have a turbulent flow. So the flow regime is determined by Reynolds number. We also have lift forces, or this is also known as monk moment. So basically, if a body is moving with a certain angle of attack in a fluid, so imagine, I'm not sure, can you see my camera? Well, so imagine that this is the body here. If we have an angle of attack, basically, and we push it forward, what will happen is that pressure will build up in front of the vehicle, and we will have here lower pressure behind the vehicle, or an area with lower pressure. And if this geometry of the vehicle is not symmetrical, or is not like a simple geometrical form, this will cause like a destabilizing effect. So if we're moving like this, we will start also going down just by this effect of lift forces. I mean, this is how planes fly. I think it's a very simple thing to model. And you can also find this term so-called cross flow drag. So this is the difference between lift and drag, basically. So we can see later that basically cross flow drag is just the off diagonal terms of the damping matrix. However, the drag of the damping matrix. Finally, the most complicated part of damping is the so-called vortex shedding. This is like, you can read a bit more about it if you like, as the D'Alembert's paradox. So basically, in a viscous fluid, the frictional forces that are present on the body or in the system are non-conservative with respect to energy. So this kind of, one of those effects are these vortex. So if you have an object with some sharp edges and you move it in the water, you can notice these kind of small vortices that start to appear. This is often also an effect that is quite dominant if we have higher speeds and if we have very rough geometries moving in a certain fluid. Okay, so how do we calculate those? Basically, just through approximations. So the way that we would calculate the damping for a certain body is, there are like two, let's say, common methods in the literature, or like common well-defined methods. One of them is just a truncated Taylor series expansion. So if you take the damping force, let's say with respect, which is a function of velocity, is basically we just take a third order Taylor series expansion and then just truncate it, for example, at the third order. Or another method that is also often used in like modeling submarines is a so-called second order modulus. So basically that this model is also kind of widely accepted. You can see here that we also multiply by the absolute value of the velocity, and this is kind of a bit inspired by the formula, or what is called Morrison's equations here. If you like, you can read more about that, which kind of relates drag to be the function of the surface area of that is in the direction of the flow, and a certain coefficient of drag, which is a function of the Reynolds number, multiplied by the density of the fluid times the velocity by the absolute value of the velocity. So this is like this quadratic term, and we have absolute value just to preserve the direction of the force. So exactly, so these are two approximations that are used. Now, if you look in the literature, you will find of modeling damping of underwater vehicles, you will find a lot of different models that have been kind of engineered together or put together to kind of fit a certain application. So here are some of them that I just reported here. So if you take a look, for example, at the equations of Fossen from '94, these are basically, he models the damping as just a linear damping matrix that kind of represents the laminar flow, and a quadratic damping matrix which represents the turbulent flow. However, this is basically like inside of this. So as I said, the diagonal terms are like the actual drag, and the off-diagonal terms are going to be what creates the lift. However, the assumption here is that we can approximate underwater vehicle to have several planes of symmetry, which is often like the classical underwater vehicles, or like these torpedo-shaped underwater vehicles would have, or you can assume that they have. Exactly. So, and that of course, that the vehicle is moving at slower speeds. So slower speeds, that's between 1 to 2 meters per second. Some other sources kind of have a little bit more complex. So this here, for example, mixes both second order Nautilus and truncated Taylor series together. There's also Mercator 2014, for example, has these matrices. So there's a linear, there's a quadratic, or a double quadratic, one with absolute value and without. This reference here is so far the, let's say, the most complex damping model. So instead of having like only 1 or 2 matrices, there are 6 different matrices, so each one with 36 elements. And another model, I don't write it here because it's a little bit too complicated. It's back from 1967, which models was used like heavily for underwater for submarines. That was kind of a classified thing, but then it was released afterwards. And some other references you can go through if you like to like have different representations of the drag. Okay, so that's it for hydrodynamics. If we now take all of these stuff that we just talked about, put them into one model, we will arrive at the full equations of motion of an underwater vehicle. So the kinematics part that I just talked about earlier, we are only concerned with velocities, transformation between the different frames, and the dynamics part we also put together here. However, I will explain a little bit why do I have this VR. So first of all is the rigid body terms, which we derived earlier, then all the hydrodynamic terms, which is the added mass and the damping, so I keep here as a nonlinear function, the restoring forces, and I've added here another term which is an unknown term, what I call unmodeled effects. So all of that summation of forces, or MA basically, is equal to all of these forces, equaling here the tau or whatever actuation forces that we can put on the vehicle. Now here, of course, comes more terms, which are like disturbances. Anything from ocean currents or any kind of disturbances can be added on top of here if we can model it. Now you notice here that I changed also a little bit. So here there's V and there's VR, and VR basically is the velocity of the body with respect to a fluid, or with respect to we call it the water relative velocity. So if there is, assuming that there is an irrotational current, since we are always modeling the rigid body dynamic with respect to an inertial frame, so we will always have the velocity with respect to the inertial frame in the rigid body part. However, in all the hydrodynamics, the velocity of the fluid with respect to the body has to be considered. And we often assume uniform or fixed, basically, ocean current with only linear parts. So we cannot really model underwater vehicles in hurricanes, or if we have a rotational current. So this is the assumption here. This is just a linear ocean current. We assume over a certain period of time that this current is fixed. In case you can measure it, you can always add it here, and basically just the total velocity minus this velocity of the current is going to be giving us the relative order velocity. And this goes into the hydrodynamics part. Now, if we assume that this is that this is fixed, so actually the acceleration here, this acceleration part is going to be equal to v dot. So this term cancels out, and then we just can add those two together. However, we cannot do that here. Okay, any questions? So far?
Yeah, I have a question. So you have the kinematic model and the dynamics model. From the literature, I saw that there's also solutions based on solely the kinematics model. I was just curious. Do you think that's really something that's good enough?
Okay. So if I understand your question, so you say like, why don't we only use the kinematics model? Why do we need a dynamics model?
Well, I understand that the dynamics model is more accurate, but do you think the kinematics model would be useful in for example, open ocean cases, or I was just curious on your thoughts on where to use kinematics and where to use the dynamics model.
So basically, if you want to be the most accurate, you have to use them both together. So since these are like 6 equations or 6 differential equations, they could become 7 if we're talking about quaternions, and these are another 6 differential equations. You will have a total of 12 differential equations, so this would be the full model. So assume that you just want to simulate a certain model here. You have the dynamics, you are applying forces. So whenever we are talking about forces and the forces are changing, the kinematics is not enough to describe these formulas. So if we are talking about so we don't have acceleration, we just are in some kind of a perfect world where velocity can change directly. And the way we actuate our robot is by just giving it a velocity command, and then we assume that it will directly obey. We say, okay, move at 1 meter per second, it will directly move at 1 meter per second. You can ignore dynamics and work only with kinematics. So as long as you're not considering any forces for your robot, or you assume that it is living in a certain world that only velocities are your reality, you could just get away with the kinematics. As the moment we start to introduce forces, the moment we have, in the end, an underwater vehicle has to be moved in a certain way. We often use thrusters or some other kind of actuators that we're going to see next. These things become dynamics, and then we start having, when we have forces, we have accelerations. When we have accelerations, we have dynamics. So it depends on what is your application. So if your application is, you have a vehicle that is supposed to go only for very long ranges, and it is always going with a fixed forward speed, you can neglect the small time it took to reach that speed, and if you can guarantee that your robot is moving always with a fixed speed. So this is also part. So then you can just deal with the kinematics. However, if you want to do a bit more complex maneuvers, like what we saw earlier in the talk of Professor Kirchner, if you want to do docking, if you want to do any kind of control, without the dynamics, I think it's way harder to approach.
Yeah. Okay. Thanks.
All right. Any other questions?